Hello.
Yes, sir.
Mhm. So we can start our today's lecture. The discussion, you can continue the discussion on SVM. So in our last class, we have discussed one example, this example, and so far what we have discussed in support vector machine. So in our first lecture, we have discussed about that is the different elements of support vector machine. Okay? What is support vector, and then why we call it support vector, and then what is hyperplane and the equation of the hyperplane, and then uh, that is what is margin and how can we define the margin. So these concepts, and then we have discussed that is the solution approach. We have derived the equation of SVM with hard constants. That means one of the optimization equation that is the objective of our support vector machine. To solve that optimization problem, we have also introduced the Lagrangian method, and then details of the Lagrangian method, the derivation of different equations we have discussed, and then we solved one of the problem uh, that is using our Lagrangian approach. And in our last class, we have started discussion our that is why hard constants is not enough, why we need the sub constants, SVM with sub constants, and we derived the equation for the SVM with sub constants. And then we discussed one of the example. This example and the solution approach of the approach, but in different manner or different way. Okay, different way. So now I want to start also from this example. That is this example. Okay. So in this example, we can see that if data sets are given and if we plot the scatter plot, then maybe we will get this kind of uh, that is plot. And in this side, we have both the negative and positive. Okay, negative and positive samples. So both negative and positive samples we have, and using those from the negative and positive samples, at first what we have to do, uh, we have to select our support vectors. Okay, so we have considered that this one is one of the, and this one that is usually the number of support vectors. It is number of dimensional data, two-dimensional data. That means we need to consider like d plus 1, here d is 2, that's 3 support vectors for this case. It is a standard, or at least we need to select at least 2 support vectors, at least 2 support vectors for this purpose. Okay, so we have the support vectors, that is this one. Consider that this one is S1 and this one is our S2, and here this one is our S3. This one is our S3. Then we can draw different kinds of hyperplane. And as we have just two-dimensional data, then in this case the hyperplane will be just the line, okay, just the line. So now which one will be our perfect hyperplane, or we can say the optimal hyperplane. And to find out that, at first we have to do the augmentation, okay. That means we have selected these support vectors S1, and the S1, you can see that S1, the vector is 2 1. Here is X1 is 2 and Y1 is 1, so that's why it is 2 1. And then the S2, the support vector, it is 2 minus 1, and S3 is 4 0. So if we do the augmentation, then we have to add another dimension, and that dimension we have to just place 1. So that means 2 1 1, 2 minus 1 on 1. So after augmentation, we will get these support vectors S1 tilde, S2 tilde, and S3 tilde. In third dimension, you can see just we put the 1 for the augmentation purpose. The next, what we have to do, the next, um, after augmentation, we have to form the Lagrangian equations. These are the Lagrangian equations. And last day I also discussed about that is how it is similar to our Lagrangian equation that we have discussed in another lecture. Okay. So first equation we will record for our support vector 1, and second equation we will record for our support vector 2, and third equation we will record for our support vector 3. And in first equation you can see that S1 is fixed. Okay, that is the S1, here's the S1 is fixed. So that means support vector 1 is fixed, and support vector 1 is from our negative class. And then support vector 2 here, the support vector 2 next is support vector 2, and we can see support vector 2, we fix the support vector 2 here, and support vector 2 is also from the negative class, and support vector 3 is there, that is support vector 3 is from the positive. And we can see that first equation is 1 fixed, S2 fixed in second equation, and third equation S3 fixed. And then we change the variables like S1, S2, and S3. Here is S1, here is S2, and here is S3. And here is also S1, S2, and S3. And here with S1 we have to consider alpha 1, with S2 we have to consider alpha 2, and S3 we have to consider alpha 3. Uh, so, but how we got these equations, we have discussed those things in our there is the Lagrangian optimization method discussion. Okay. Now what we have to do, we have to put the values of S1 tilde is and S2 tilde and S3 tilde. That means all the augmented support vectors values. So here is that is, we know that the S1 tilde is 2 1 1, S2 tilde is 2 negative 1 and 1, S3 tilde is 4 0 and 1. Then we can see there is the equation we will get alpha 1, and this is S1 and S1, then S1 and S2, and S1 and S3. Okay. And now what we have to do, you can see these are the two vectors. We have to multiply these two vectors. Okay. So here is the dot product. We can see 2 times 2. So 2 times 2 is 4, then 1 times 1 plus of 1 times 1. So it will be 6. 6 alpha 1. Then for the second one it will be 2 times 2, this also. Okay, 3 unknowns. So 3 unknowns are there. Okay, then the three equations and three unknown, that means we have to determine alpha 1, alpha 2 and alpha 3. Then if we solve these three equations, then we will get alpha 1, alpha 2 and alpha 3. And here it is, that is alpha 1, alpha 2 and alpha 3, we got those values. That means we got the values of Lagrangian constants. So if we know the Lagrangian constant, then we have to use that to find out the W. And we can see here W tilde equals summation of alpha I and Si. And that is, now we can put the values of alpha 1 and then S1 and then alpha 2, S2 and alpha 3 and S3 also. Okay, alpha 3 and S3 also. And then if we put those values alpha 1, alpha 2 and alpha 3, then we will get the finally we will get this equation. Okay, this equation. So in this in this vector you can see that is the first two values, it is our W, and the last one is B. Okay, last one is B. So now we can see here W and B. So W is given and B is also given. Okay, so we got the W and B. Now we need to form the hyperplane equation. And hyperplane equation, we know that it is W transpose X plus B. So W is 1, 0. So here is the 1, 0. And X is X and Y. And B is our negative 3. So we can see here, if we put the values of B, and also if we multiply 1, 0 with the vector X, and then we will get X minus 3, that is X equal 3. So this is our hyperplane equation. So this equation, it is telling us that this equation is a line parallel to our y-axis at point 3, okay, of x-axis. So you can see here at point 3, this is a parallel line. Okay, so this is a parallel to our y-axis, that is x2. So this is our hyperplane. Okay, and now next what we can do, we want to test, that is, maybe we have some test points and we want to find out the class levels of those points. And for that, what we have to do, we have to uh, place our the data point in our line. Okay, so this is the line we have, W transpose X plus B, that is the hyperplane. So if we put the X equal 1 and 2 and W we know and B also we know, then after solving this we will get negative 2. Here sign is important because sign mentioned that is the class. So here negative sign means negative class. It means that it is negative class. That means 1, 2 is negative class. So we can check whether this is wrong or right. Okay, so now if we can see here, there is 1 and 2, x1 is 1 and x2 is 2. That means that the point we will get at this point. And this side is negative. Okay, this side is negative. Previously we know, we assume that this side is negative and this side is positive. So that's why the S1 and S2 we assume that those are from negative class. Okay, so here this is the negative side. This point is negative side. Okay, that means it is true that this is negative class. And another point is 6, negative 1. So if you consider this point, if we put the value here, then we will get the 3. So it means that this is a positive class. And we can see if we place it here in this plot, then we can see 6 minus 1. So here is the 6 and minus 1 is this. This is the minus 1. Okay, so that means the point we will get at this location. So this is 6 minus 1. Okay, 6 minus 1. And we can see it is in positive side. So that means the hyperplane equation truly recognizes the positive class elements and negative class elements. So that's we have to do using our support vector machine. Okay, support vector machine. But so far we have discussed the linear problem. Okay, linear problem, that means linearly separable problem. So sometimes we will get the data, those are non-linear. That means we will not get any just a linear line to separate positives from the negatives. Like in this example, we can see that the blue dots or blue circles, those are negative points, and red squares are just positive points. So we cannot draw just a linear line to separate positives from the negatives. Okay. So what can we do? We can draw something, some polynomials, like maybe the circle, okay, equation of a circle, and that circle can maybe separate positives from the negatives. But SVM, it has some different approach to deal with this problem. So it will not draw the polynomials. So what it will do, it will try to transform those there is data points into a new dimensional space, okay, new dimensional space, and on that space, we can see that those points we can select linear, we can separate not linearly, okay. That means uh, we have to transform these points in such a way so that after transformation we can use the linear separation, and that means linear separation SVM. Then how can we do that? So one of the approach, it is mentioned in the book, that is, okay, maybe blue class vector, these are the blue class vectors and red class vectors, okay. So that means these are the negatives, okay, these are the negative blue class vector, and these are the positives. So you can see this point is actually the 1 1, okay, 1 1, this is blue class, that is negative. So is this 0 2 is there, and 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 now what we can do here, here the blue class vectors and red class vectors. We need to, and what's the transformation function, okay. So this transformation function is proposed in the book, okay. So that means if we apply this transformation function, then we will get those points in a new dimensional space. Like here, let us transform the blue and red class vectors using the nonlinear mapping function. Here is it is phi. So it means that if we pass the x1 and x2, if this condition is true, then we will transform the values like this way. Okay, so at first we can see that 1 and 1. If we pass the 1 and 1 here, then here is 1 square plus of 1 square. Okay, so whether this one is greater than equal to or not. But now we can see that it is square root of 2, which is actually not greater than 2. So that means this condition is false. Okay, this condition is false. So if this condition is false, then we will keep the data point as it is. Okay, x1 and x2. So we will keep the data point as it is. So now we can see that that is blue class vectors. That means 1 and 1. If we apply this mapping function, it will not change. Similarly, if we apply to this data point, that is a square root of minus 1 square plus of 1 square. So whether it is greater than equal to or not, you can see 1 square, here is 1 square. It is square root of 2 greater than equal to. Is it true? No, false. So that means if false, then we will not change. We will keep it as it is. Similarly, for this data point also, for that data point also, the point will not change its position. Okay, so it will remain on the same position. Now think about the red class vectors. The red class vectors, in this case we can see these are the red class vectors. If we pass this one here, then it is square root of 2 square plus of 0 square greater than equal to. So you can see here square root. So that means it is 2. 2 greater than equal to. So actually this is true. Okay, this is true. So we can see that if we pass this vector here, then we will get what? We will get, that means we have to apply this equation for the transformation. Okay, and it is 6 minus x1, and we can see that for this vector, the x1 is 2. This is our x1, and x2 is 0. Okay, x2 is 0. So x1 is 2 and x2 is 0. So if we put the x1 is, we can see 6 minus x1. So 6 minus 2 plus of x1 is 2 minus of 0, that is x2 is 0 square. And here is a 6, again 6, x2 in this case is 0, and x1 is 2, and x2 is also 0. Then we will get this. Okay, we will get this, that is 8 and 10. So it means that this data point will transform to a new space, that is 8, 10. Similarly, if we pass this one, the second data point, at first we need to check the condition, and we can see that it is square root of 0 square plus of 2 square greater than or equal to or not. So we can see here it is 2 greater than equal to, so that means this condition is true again. If this condition is true, then we have to apply this equation for transformation. Okay, so now in this case x1 is 0 and x2 is 2. X2 is 2. So here is this. Therefore, if we pass 0 to, then 6 minus 0, so we will get what? We will get 10, 8. Similarly, we have to pass this one, test this one with our condition, and here is the condition, and you will get that both of these are true. And if we apply our transformation function, then this point you will get here, that is a new space 12 and 10, and this point will transform to a new space, that is 10 and 12. Now we can see that so blue class vectors and red class vectors. The blue class vectors actually didn't change the position. Okay, but the red class vectors change the position. Previously 2 0, so we can see the 2 0 is this one. It is now changed to a place, that is 8 10. So we can see here 8 and 10, that means this is the position of that. And now we can see another, that is 0 2. So 0 2 is 10 8. So here is the 10. 10 8. So here is the 10 and 8 is this. That is, this is the place. Okay, this is the place. So 2 0 now you can see it is here in 10 8, 10 8 1. Similarly, other 2 points we can see also, that is, we can see here. Okay, now so that means now we can see if we can see here, that is blue class vectors and red class vectors are now linearly separable. Okay, linearly separable. And for the linear separation, what we can do, apply the method we have discussed already. Okay, at first maybe we need to think about the support vector. So in this case, we can consider this is one support vector. This is our S1, and we can consider this is another support vector. This is S2, and this is our another support vector is S3. So these two are from positive class, and this is negative class. Okay, and now we can actually apply the method we have discussed earlier. So directly we can apply that method for our hyperplane. Okay, hyperplane. And that means at first we need to augment the support vectors. So we will get s1 tilde, s2 tilde, and s3 tilde. And then using the s1, s2, and s3, we have to form the Lagrangian equations. And then we have to solve the Lagrangian equation and find out the values of alpha 1, alpha 2, and alpha 3. And then based on the alpha 1 value, alpha 2 value, alpha 3 value, and s1, s2, s3, we can find out wi. That is w, it will be w. Uh, W, you will get W equal 1, 1 and B equal negative 10.057. Then using this, we need to find out the equation of our Lagrangian equation of our hyperplane. So it will be a hyperplane equation will be, that is the W transpose X. So consider that X here, look, okay, like X plus of B equals 0. Okay, so this equation, and in this case we can see W transpose. So here it will be 1 and 1, and for X we will get the
স্যার
and then plus
ভিডিওর
of
স্যার মাঝখানে একটু অফ হয়ে গিয়েছিল আর কি, শোনা যাচ্ছিল না।
acha, okay, I can repeat it. Okay, so by solving our Lagrangian equations, so we will get again the three equations, and the alpha 1, alpha 2, and alpha 3 we need to know. From the three equations we will get the values of alpha 1, alpha 2, alpha 3, but just by solving those equations. Okay, because we have three unknowns and three equations we have, then we will get that. And then we have to apply the equation, that is to find out w tilde. We have to sum up alpha I and s I tilde. Okay, so wi and s I tilde for all support vectors. So we have three support vectors, so we have to add this. Then we will get the value of w and also b, w and b. Then if we get the w and b, the next thing is we have to find out the hyperplane equation. So how can we find out the hyperplane equation? We know the hyperplane equation is this: w transpose x plus b. We have formulated this in our first lecture. So w transpose x plus b. So here w transpose w is what? This is our w. One transpose it, and x is x and y, and b in this case it is negative something. Okay, so that means negative 10.057 equal 0. So then if we multiply these two vectors, this one and that one, then we can say it will be 1 time x, that is x, plus of 1 time y, that is y. So x plus y minus 10.057 equal 0. So this is our This is our hyperplane equation. Okay, x plus y minus of 10.057, our hyperplane equation. If we draw that hyperplane, then we will get this. Okay, this will be our hyperplane. I think you know how to draw a line from equation. Okay, the equation is given, then how to draw the line from the equation. I think we know that. So here is this. Then and we can see this is our hyperplane. Okay, the support vectors. And now we can what we have to do next. If we get any point, okay, any point as a test point, then for the nonlinear SVM, what we have to do, the test point at first we need to transform the test point, okay? And uh, then we can see, then we have to apply to our hyperplane equation. Then if it provides us the positive, then positive plus. If it provides us the negative value, then just negative plus. So this is how the nonlinear problem we can solve the nonlinear problem. But the problem here is that is we already mentioned that we need to find out the equation. That equation usually we call it kernel trick, or you can say mapping function. Uh, so we need to find out the mapping function or kernel trick, and this is not universal. That means we can say that every problem we can use this function to transform. That will not work actually. So that is the case here. That means for each and every problem for different data set, we need to think about different types of kernel tricks. There are few benchmark function that is called, we call it kernel function. We will discuss those also. Uh, but those are also not enough. Okay, not enough. Sometimes you need to build the kernel trick by yourself. Okay. Uh, so now think about like the same problem here, the same problem. Can we think it differently? Can we think like uh, different approach or different function to solve the same problem? Because in the book it is given, the solution is given. But can we think about that is it is maybe differently? Yes, we need to think differently because maybe uh, in your case you will find the different solution. So like one thing I can mention here, that is how can we solve the same problem in different way or different manner. So what's the target here? The target is uh, we have to transform the data points in such a place so that we can maybe apply the linearly separable hyperplane. So that's the target. Okay. So if that is the target, can we think about like maybe you can say that is uh, we want to shift um, the red circles, the red squares, maybe this side, this one also this side. Okay. Then this one is also in this side, in this side. Then we can see the if all the red squares we can shift in right side, and then we can apply like maybe here linear separable. Okay, so all the red squares we will found in right side, and all the that is our blue circles we will get on the same position. Can we think like this this function? I think we can think about like this because uh, so here the red class vectors are given, and we can see that for this point, it is actually the x is 0. Okay, for this point x is 0, and for that point the x is 0. So can we write a function like this? If here is, we can say x is 0 for a point like x equals 0. If x equals 0, if x equals 0, then what can we do? We can maybe increase what? If x is 0, So we want to shift it this position, okay, this position. So that means we need to increase the x value. So that means we can say x equal the previous x plus of maybe 7 or something, okay. uh, so at least we can say at least we have to increase more than 1, okay, more than 1. So that means x equal x plus 7. So we will get it maybe somewhere here. And do we need to change the y? For that case we need to change the y. Actually no need to change the y. So if y is fixed, that means here we can see that the y is 2, and if we just want to shift this one here, then no need to change the y. So we can keep the y as it is, okay. So that means if x equals 0, then we can just use this transformation, x equal x plus 7 and y equal just 1, okay. Then if we apply to our data set, so in this data set if we apply, then we can see this point here is x is 0, and this point x is also 0. So in this case we will get this point will be this one will be what, x equal x plus 7. So x is 0, x equal x plus 7, it will be x is 0, in this case x is 0 plus 7. So that means this point we will get here the x7. You can say maybe you can say we will get here the x7 where x equals 7. Similarly, for another point, this one, what we can say here, there is a x is here x is 0, okay, x is 0. So then if we apply condition x is 0, yes, true. So x will be x plus of 7. So x plus of 7 means x is 0 in this case. 0 plus 7 is 7. So you can see here it is 7. So that means this point also we will get here. We will get here. And now we can see that we have these 2 points already we have shifted in right side. Now we want to shift like this one. So if we want to shift this one, then we can see the condition must be condition. We can see in this case y is 0, okay, y is 0. So then we can write a condition like if y is 0. If y is 0, then what we have to do? We have to change also the x. That means we have to take it in this position. So take it in this position. So again, we can say we have to apply. If we apply the same equation, that is x equal x plus 7, x plus 7, and y equal. No need to change the y. Okay, so change the y equal y. So on that case, this point will be like x equal x plus 7. So x equal x plus 7. Currently the x is minus 2 and plus 7. So it is now 5. So it is now 5. So that means we will get the same point at 5 0. Okay, y is 0, 5 0. So you can see we will get 3 4. Maybe we will get the point at this location. Okay, at this location we will get the point at this location. So that means a red circle. This red circle will move to here. And then we can see also that there is negative 2 and 0. So we have applied this equation, but this data point, that is 2 0, has also the same, it also meet the same criteria. That means this is also meet this criteria, y0. So here is also y0. So that means we have to transform, also transform this one using the same equation. So if we apply it to here, then x equal x plus of 7. On that case, x equal, currently x is 2 plus 7, that is 9. 9 and y it will be the same. Okay, so x is 9. So that means we can see this is 7, 8, 9. So we will get this that point in this position. So that means this point will now shift it to this location. So we can see that if x equals 0, or we can say that means, or y equals 0, the same equation. Okay, because the same equation, you need to form same equation, so no need to write it again. So x equals 0 or y equals 0, then x will translate to a data point that is x plus 7 and y equal 7. If we apply the simple trick here, then we can see that already uh, the separation is done. Okay, that is in left hand side we will get the that is the blue circles, and right hand side we will get here the red squares. Okay, so now we can again what we can do, we can apply our linear SVM to find out the answer of our that is the hyperplane. Okay, hyperplane. So this is how we have to try. Okay, that means no need to remember anything, just intuitively we have to do, we have to find out the trick for transforming those data points into a new dimension. Okay, new space. So that's called the kernel trick or mapping function. Okay, so we need to find out some sort of mapping function uh, to, to, to convert the nonlinear problem to a linear problem, and then we need to apply the linear SVM to find out the solution. So I hope you understand the policy. Okay, the policy. There are several kinds of tricks we need to apply. Okay, uh, but remember that yeah, we have to develop the tricks. Okay, so now we want to discuss about some kernel functions. That's our benchmark kernel functions. Usually that is also developed with SVM. Okay, those kind of kernel functions. So the purpose is the same. That means instead of developing the kernels by yourself, we want to propose some kernels that is for generalized data set. Okay, for generalized data set. And again, as I already mentioned, it has the limitation. That means so it will not perform always better, and that's why different SVM kernels are proposed. Okay, different SVM kernels are proposed. So now we can see that the one data set we have, if we have this data set, sorry. So if we have this data set, okay, we want to classify the red circles from the green circles. Consider the red are just the negatives and blues are the positives. So it means that actually it is not possible to just draw a single line to maybe separate the positives from the negatives. Okay. So what can you do on that case? Maybe solution is the polynomial. Okay. So like this kind of polynomials, if we can draw, but again, SVM will not do that. So it will try to transform the data points in a new subspace, new feature space, and then it will try to apply the linear SVM. There are several kernels for that, and one of the kernel function usually we call polynomial kernels. Polynomial kernel. Okay. So how polynomial kernel will work? Okay, so the polynomial kernel, the equation of the polynomial kernel is this. That is a times b plus of r power d. So here d is our polynomial, and b is our A and B. And so R, A and B, so those are A and B and R, okay? So now, actually for polynomial kernel, we can define the value of D. So this kernel function like D, it is the power of the polynomials, okay? Power of polynomials. Sometimes you can see that like maybe D equal 2 will work, sometimes D equal 3 will work, sometimes maybe D equal 10 or D equal 25, sometimes we need to maybe assign. That is the degree of polynomials based on the complexity of the data. Uh, so then what it will do, this polynomial kernel will actually uh, transform those data points virtually to a higher dimensional space. So higher dimensional, that means if we have one dimensional data, then it will convert to a two dimension. If we have like maybe two dimensional data, then it can place to a three dimensions like this. That means higher dimensional uh, space. The polynomial kernel will do that. So how it will do that? If we can think about like consider the d equal to. So that means degree of polynomial. If we consider d equal to here, this is the d equal to, and consider that this is the constant here r. So r is just half. So these are user defined. Okay, usually we define. We have some default values, but usually we can define those values. Right here, half or one. That degree you can select like 10-degree polynomials. Now, if we consider about just 2-degree polynomial, then see what it will do actually. Uh, so for this, we can see a times b plus half and then a square. Okay, so what we can write this a times b plus half and a times b plus half. That is 2 times you can write because here is a square. We can write this one. And now we can see that here is the a times b and here is the a times b. Then if we multiply these two, then we can write here this one is actually a square and b square. Okay, so a square and b square and plus of here is the a times b and here is the half. Okay, so we can write half ab plus of here is the half and then here is the ab. Then we can write the half ab. Then plus of here's the half and here's the half. That means 1 by 4. We can write 1 by 4. So that means a square b square. From here we can write a square b square plus here is the half ab. Here is also half ab. You can write this one as that is half and half 1 ab. So ab plus of 1 by 4. So we can rewrite this one as ab plus of a square b square and then 1 by 4. Okay, 1 by 4. That means this one is here. ab a square b square plus of 1 by 4. And now we can see that we can write this one in vector form. So here is this a square and half. So we can write a square and half. And another vector we can think about b square and half. So if we multiply these two vectors, then we will get again the same thing. Okay, the same thing we will get. That is ab, then a square b square and half 1 by 4. Okay, so we can write this one in vector form. What does it mean? It means that actually, if we have the data, then the first dimension data it will be the same that like a. In second dimension, the data we will place the square value of the data, and third dimension it is constant. Okay, or maybe positive class vectors and negative class vectors. You can see again b we will get the same value b square. That means in second dimension we have to place like a square value, and third dimension is constant like 2. So it means that so if we have the data set like here, consider that so this is our data set. Okay, this is our data set. Now if we can think about like this, for this data point, this is maybe we can say 1, and for this data point maybe you can say it is 2, and maybe this one is 3 like this, and maybe this one is 4, and maybe this one is, you can see, like maybe 7 or something. Okay. Now these data points, it will transform to a, you can see these are just one dimensional data. Okay, the doses in milligram. Okay, maybe you can say 1 milligram, 2 milligram, 3 milligram, 4 milligram, like this. So this is one dimensional data point. So according to our polynomials, according to our polynomial kernels, what it will do, this one dimensional data, it will place in two dimension form, that is, you can say, increased dimension. Okay, that is higher dimension. So for the data point, this data point, if we consider that this is a 1, 2, 3, 4, 5, 6, in this way, maybe 7, 8, 9, 10. Here is also 1, 2, 3, 4, 5, 6, 7, 8, 9, like this. Okay, so the first data points, you can see these are the red class vectors. So the first dimension is this, and second dimension will be get the a square. So if we consider this is a, and here is the a square, and z-axis is just half. Okay, so the z-axis will not change. Okay, that means always it will remain the half. So no need to maybe plot that. So a and a square. Then this data point, previously it has just only one dimensional data, so the value is 1. Currently, where we need to place this? So 1 in x-axis uh, it will be 1, and in y-axis it will be 1 square. So 1 and 1 square. So that means it will be the same. Here is a 1, and here is a 1. So 1 and 1 square. That means the data point we will get here. What does it mean? Previously, the data point, it was in this position, but now if we plot it in higher dimension, that data point we will get in this position. Okay, in this position. So previously we have the data point like in 2. So here is the 2. This is the 2. So this is the 2. And currently what we have to do, in x, it will remain the same, that is a. So a is 2 now. And a square is 2 square. 2 square means 4. So 4, that is 1, 2, 3, 4. So 4 is here. So we can see for 2, we will get this data point at this place. Okay. So this is our one, there is 2, 4. And then previously we have the data point that is the 3. So 3. So this is the 3. And now we can see that after the SVM kernel, that is polynomial kernel, after applying the polynomial kernel, we will get those data points in some other places. That is our 3 times 3, 3 square, that is 9. So 3 and 9, 4, 5, 6, 7, 8, 9. Okay. So that means we will get the data point maybe at this position. So this will be our the data points. Okay, so that means the one-dimensional data using the polynomial kernel, where the polynomial value d is 2, And we can see here that it is also represented in two-dimensional form. Two-dimensional form. Then what's the benefit of this? Okay, what's the benefit of this? So you can see that for this data set, if we apply the polynomial kernel, then we will get the data like this, using the d equal to and r equal half. Okay, 2-degree polynomials, and then we will get the data in this way. And now we can see that actually we can draw a just linearly separable line to separate positives from the negatives. Okay? Here is this line. Okay, here is that line. Okay, so now we can see that there is this kind of line we have. We can select. Then again we can see that again we have to, that is, if we got the new data points, then at first do the transformation and then determine the place, and then maybe uh, classify whether it is in positive side or negative side. Okay, using our hyperplane. Okay, so the r, we can also change the r value. Like if we change the r equal 1, so where is that? Yeah, r is 1, then you will get the equation a little bit different. Okay, it is little bit different. You will get the equation like this, the vectors like this. It means that previously we have the a, but after two-dimensional plot we have to change the a to a square root of 2a, and in y-axis we have to place like here the a square. Both the value of x-axis and y-axis are changed in that case if we consider r equal 1. Okay, and using r equal 1 you will get this value, this curve for the same data set. Okay, it means r has also the impact on our that is transformation. So this is called our polynomial kernel, and there are several other kernels also, like the our uh, our here is we have already discussed this one, radial basis function. Okay, the radial basis kernel. So if we apply radial basis kernel here, and the function of radial basis kernel is one kind of Gaussian kernel we call it. So this is the equation. Okay, so for the polynomial this is the equation. Using this equation it will transform those data points into new subspace, and for the radial basis function this kernel is used. Okay, e to the power minus of x minus of y square divided by 2 sigma square. Sigma is our that is the sigma is our standard deviation. Sigma square is our variance. Okay, and we can also apply the sigmoid kernel. Here is the tan h kernel using this equation. Okay, using this equation. So here the delta is mk is the constant here. Okay, and xy you can see, then apply the tan h for transformation into a new domain. Okay. So usually we call that is the radial basis function. Uh, it can place that is data points in infinite dimension, but uh, for the case of the polynomial kernel, the dimension is fixed. Okay, that means you can define your dimension. Okay, so that means we can apply either polynomial kernel, or we can apply radial basis function or Gaussian function or the sigmoid or tan h functions. Okay, so those are the traditional, or we can say that is the benchmark SVM kernels. We can apply to transform our data points. And sometimes we need to apply different kinds of tricks, as I already mentioned, like very simple trick can also convert a linear to non-linear, non-linear to a linear form. Like one data set, if you can see here, one data set. So here's x and good and bad, like good is positive and bad is negative. Okay, so if we plot our data points, if we plot our data point, then data point will be like this, and we can see that it is not linearly separable. Okay, so we cannot, maybe if we can apply the SVM without kernel, then we will not get better solution. Then the simple trick, here we can see that there is the simple trick. That's why the trick is necessary. So if we do something like the square root of x, so instead of x, if we put the square root of x, then the data point will be like this, and we can see that just simply square root of x make the problem linear. So on that case, maybe you need to think about, like, when we plot something and then observing those values, then we have to decide that what kind of trick we need to apply here. Can a very simple trick convert our non-linear problem to a linear one? And on that case, maybe the uh, complex Gaussian, or we can say radial basis function or polynomial function. Uh, so no need to apply those kind of kernels on that case. Okay. So now we can see this problem we can easily separable. Okay, the easily separable problem. Another data set. Uh, so this is another data set. We can see again here the good and bad, or we can say that this is positive and negative. And we have the x1 and x2, in this case two-dimensional. That is x1 in this dimension and x2 in this dimension. And the data points are good and bad. Okay. And based on that, we can see that it is not possible to separate using the SVM. So what can we do? Can we define a simple kernel tree? So here we applied a simple kernel tree. That is the G, and then the x1 square, and then summation of the y1 square. Okay, so that is here x1 square and then summation of y1 square. And if we just convert our dimension here in G dimension, okay, and then based on the G, if we plot good and bad, then we will get the data point like this. So now we can see that again, again, uh, we can separate our data points using the linear separation. That is our linear hyperplane. So that's what we have to do in our SVM. Usually in our examination, the data sets are given. Okay, data sets are given, and you need to find out what you need to find out. Maybe if you can see that the problem is non-linear, then you have to convert that one to a linear problem, defining the kernel tricks. Okay, so you need to define the kernel tricks by yourself, and then after that you have to apply our linear SVM, to solve the problem. Okay, to solve the problem, that is to find out our problem. So on that case, it is better to apply the method that is the we discussed in Lagrangian approach. Okay, the Lagrangian approach. So that means the tabular method we have discussed. So this tabular method, okay, this tabular method, that because it is very clear, okay, very clear, because we have already developed these equations and also apply those equations to solve our SVM problem to find out, and using the alpha and SI to find out the omega. Okay, find the omega. So that's all in our SVM discussion. Anyone have any question?
স্যার আমাদের কি কোনো কুইজ হবে?
কুইজ একটা তোমাদের নিয়েছি, সেই একটা রেজাল্ট এখনো দেইনি। হ্যাঁ, রেজাল্ট আমি একটু দিই, তারপর দেখি যদি তোমাদের মানে ভালো মার্কস না হয় তাহলে আরেকটা আমি কুইজ নিব।
ওকে, থ্যাংক ইউ
বেস্ট
স্যার।
অন কাউন্ট করবো তো, সেজন্য হচ্ছে আমি একটু দেখি এটা। ওকে, ঠিক আছে।
ঠিক আছে স্যার।
ওকে, so any other issue? Okay, thanks everyone for joining this session. See you in our next class. Thank you.
Thank you, sir.